So today we will be talking about basic graph algorithms. Last time we did an introduction to graph algorithms, and we talked about graph representations, adjacency list, the adjacency list and the adjacency matrix. And we talked about the advantages and disadvantages of each, and we gave an example of an operation that can be done more efficiently using an adjacency list, and an operation that can be done more efficiently using an adjacency matrix. Now our default graph representation is going to be the adjacency list. So we will be assuming that the graph is represented as an adjacency list, and that's for a reason. We will see that in the graphs, in the graph algorithms that we will be studying, we will always need to traverse the list of neighbors of a given vertex. So we are at a certain vertex. When in processing that vertex, we will need to have a list of neighbors for that vertex and traverse that list of neighbors. So that's why the adjacency list will be our default graph representation. Okay, so today we will be talking about basic graph algorithms, breadth first search and depth first search. Now I assume that you are familiar with these, so you know them already, but here we are trying to gain a deeper depth, a deeper understanding of depth and breadth first search algorithm. The basic search algorithms, we would like to understand them deeply because they are the foundation for other graph algorithms, and because it's our objective is to gain strong and deep enough understanding of these algorithms that will allow us to use them in solving actual problems. Okay, so we will start with just a high-level distinction between breadth and depth. So if I have a graph like this, so if I have a graph like this, then a breadth first traversal of this graph, suppose that we are starting from this vertex. So if I start from this vertex or node, if I want to do breadth, then this is going to be my first vertex. Then I'm going to do the two vertices that are the nearest neighbors of my source or root vertex. So if I start from this, then in doing breadth, now I'm doing breadth. So I'm going to do, this is going to be 2, this is going to be 3, because these two are at the same distance from 1. So each one of them is only one edge away from the source. Then I go and visit the vertices that are 2 edges away from the source, like this, for example, this could be number 4, and this is number 5, and this is number 6. Okay, and then this is going to be number 7 because it's 3 edges away from the source. So this example simplifies things, but just to explain the basic concept behind breadth and depth. Now this is breadth. Now if I want to do depth first search, and I start from the same vertex, this is going to be number 1, but then I will be going in depth. I will take some neighbor of 1 like this. This could be number 2 as well, but then I will be going in depth. So then I will be going to this vertex maybe. This is going to be number 3. Then I will keep going in depth until I hit a vertex that either does not have any neighbors or all of its neighbors have been visited already. So I will, once I hit a vertex like this, I will go back. I will backtrack, and I will go to this vertex at level at this depth, and then I will possibly go to this vertex, and so on. So I'm not trying here to describe the details of depth or breadth. I'm only trying to give a high-level idea of each different search algorithm, so that we can distinguish between them and understand at least at this point have some understanding of the different uses of these algorithms, what each algorithm is used for. For example, if I ask you which of these two algorithms is used for finding the minimum distance from a given vertex to other vertices in the graph. So which one is it going to be, breadth or depth? So which algorithm should I use if I'm interested in finding the shortest distance, the shortest unweighted distance, the shortest unweighted distance between the source and a given vertex in the graph?
Breadth?
Breadth, yeah. Because breadth is by nature first looks at the vertices that are at distance 1, then it looks at the vertices that are at distance 2, and so forth. So in fact, the main purpose of the breadth first search algorithm is to find the unweighted distance between a given source and any other vertex in the graph. Okay. Now, our definition of unweighted distance is the number of edges. So when we talk about an unweighted distance, it's just the number of edges, as opposed to the weighted distance. What's the weighted distance? So if the unweighted distance is the number of edges, what's the weighted distance?
Total edge weights.
I'm sorry? Yeah. Yeah, it's the sum of the edge weights. So when your graph is unweighted, it only makes sense to talk about the unweighted distance. But if your graph is weighted, both make sense. So you can talk about weighted and unweighted distances, because even if your graph is weighted, the unweighted distance can still make sense, because it counts the number of edges between two vertices. And basically, when you do the unweighted distance in a weighted graph, you are ignoring the weights. So you may need certain operations that you apply to a weighted graph have nothing to do with the weight. So they don't need to use the weight, so you can compute the unweighted distance. So the unweighted distance can make sense in a weighted or an unweighted graph. But obviously, the weighted distance makes sense only if the graph has weights. Or in fact, you can think of the unweighted graph as a graph in which all edge weights are unity. All edge weights are 1. You can think of an unweighted graph like this. So anyway, now what's depth first search used for? Depth first search is usually used to study the structure of a graph and give some information about the relations between the different vertices in the graph. For example, it's a good algorithm for detecting loops or cycles in the graph. That's one basic use of DFS. We will also look into other uses of DFS, like topological sort, in a later lecture. Okay, so this is depth versus breadth. Now we will just focus on breadth. So most of this lecture is going to be about breadth first search. And we will use this graph as an example. So we are given this graph. In breadth first search, or BFS, we are given a graph, and we are given a source vertex or node. Like in this case, the source may be A. So we are given this source, and the objective is to do a BFS in order to find the minimum unweighted distance from the source to any node in the, or to every node in the graph. Okay, every vertex in the graph. So we will see how we can do this. So initially, when we initialize this, we know that the distance from the source to itself is going to be 0. And distances to other vertices, we will initially set them to infinity. Now, what's infinity? Infinity in algorithms, whenever we use infinity, what does it mean?
Always greater. Always greater.
Yeah, a sufficiently large number. A sufficiently large number. What is sufficiently large? Sufficiently large depends on the algorithm that we are working on. So in this case, what is a sufficiently large number for that can be infinity, that can be viewed as infinity in this case? So it depends on our objective. Our objective is to find the minimum unweighted distance. So a sufficiently large number should be larger than any unweighted distance in the graph. So what do you suggest here? How can we compute a sufficiently large number?
Total number of edges.
Yeah, exactly. So we can calculate the total number of edges plus 1, because a path in the graph can have, all the edges in it. So to make sure that it's larger than any path, than the largest path in the graph, we will just do the total number of edges plus 1. Plus 1. So that's going to be our infinity in an actual implementation of the algorithm. When you translate this into actual code. Okay. So now let's see. So this is a review question. In doing BFS, what's the auxiliary data structure that we use in order to get breadth?
Q.
Yeah, we use a Q. Exactly. So some people still remember that in order to do BFS for a graph, we use a Q. And now it will become, as we go through this example, it will become obvious why the Q is the right data structure for doing breadth. And in fact, why the stack is the right data structure for doing depth. Well, we don't have to worry about the stack today, but it's this is just, these are fundamental facts. If you want to do breadth, you use a queue. If you want to do depth, use a stack. And now, as we go through this example, it will become obvious why the queue will give us breadth. So we start by we have a queue, and we put in the queue we put the source, which is A. So we put A in the queue. Then we dequeue, we take the element at the top of the queue, which is in this case A, and then we enter into the queue. What do we enter? What do we enqueue? So we dequeue the A and we enter, we enqueue
B.
only B. Why B?
All the nearest neighbors.
All the neighbors, yeah. All the neighbors, all the vertices in the adjacency list of A. All the neighbors. So that's why, the adjacency list is the natural graph representation that will serve us very well here. So just look at all the neighbors, B and D. So we put B and D. Now the question is, in which order should we put them in the queue? The answer is, it doesn't matter. So you can put them in any order. So different orders are going to give you different traversals but all traversals are going to give you the same distances. So when we are done with this, in a few minutes, we will see that by making different selections of or by enqueuing in a different order, we will get a different traversal, but the different traversal will still give us the same distances. Okay, so now we put B and D. Now, since B and D have been discovered as neighbors of A, so what should we set the distances of B and D to? What should we now set the distances of B and D to? To 1. Yeah, because this is at 0. So this is going to be at 1. So because we have discovered the neighbors. So now we are, in fact, we are constructing a tree. Basically, we are constructing a tree like this with A and B and D, which is what we call the BFS tree. Okay, then we just keep repeating the same thing. We DQ, we take the element at the front of the queue, and then we enqueue the neighbors of that element. Okay, so now the top of the queue, or the first element in the queue, is B. We take B out, and we put its neighbors in the queue. Now the neighbors of B are C, but what about A? Isn't A a neighbor of B?
Already visited.
So how do we know now? Algorithmically, how do we know? How do we distinguish between C that has not been visited and A that has been visited?
0.
Yeah, exactly. We look at the distance, the current distance. So this current distance indicates that we have seen this. We have given this a distance, so we have visited it. While this is still at the initial value of infinity, which means that this has not been touched yet. Okay, so we put the ones that have not been visited. So we only put C, we do not put A again. If we put A again, what will happen?
It will be an infinite loop.
It will definitely, it will never terminate, right? If just, even if you have something like this, a graph with 2 nodes and 1 edge, this can cause an infinite loop, because you will find B in the adjacency list of A, then you will find B in the adjacency list of A. Then when you look at the adjacency list of B, you will find A in it. But then when you, without checking, you will look at the adjacency list of A again, and you will find B in it, and it will be an infinite loop. So marking is very important in traversal algorithms to make sure that you don't visit the same node an infinite number of times. Okay, so here we take B out and we put the neighbors, and the neighbor is C. Now here's why the queue is the right data structure for doing breadth. The key idea here is that the neighbor of B was placed in the queue, so it was enqueued after D. The point is that D, which is a node that is closer to the source, by using a queue, D has reserved its its place and its order. So we will be processing D before C. So when we looked at the neighbors of A, which are B and D, we put B and D. So now by putting B and D, we ensured that B and D will be processed before any node that will be enqueued after them, which ensures that everything that is at level 1, at distance 1 from the source, will get processed before anything at the next level. What's at the next level here is C. C is at the next level because C is at level 2. So by using the queue, we ensure that nodes that are at level 2 will be placed after nodes at level 1. And nodes at level 3 will be placed after nodes at level 2. So this is the queue here is helping us order the nodes in the queue by level, order the nodes by level. Okay, so now since we discovered C as a neighbor of B, the level of C is going to be 2. Then we just keep doing the same thing. Now we take D out and we enqueue the neighbors of D, but they will be after C, because we know that the level of these nodes is going to be greater than or equal to the level of C. In fact, in this case, it will be at the same level as C. Now, what are the neighbors of D? We have 3 neighbors, A, E, H. We know that A doesn't have to be entered again because it has a distance of 0. So we check on it, but we do not enter it. What we enter E and H. In which order? It doesn't matter. Let's enter E before H. Let's stick to the alphabetical order. So if we have multiple possible orders, we just stick to the alphabetical order. So we put E, then H. Okay. Then in the next step, we take C out. Well, we forgot to set the distances of E and H. So we set the distances of E and H to 2, because they were entered into the queue as neighbors of D. So they're neighbors of D, so their distance is going to be the distance of D plus 1. Okay, so now I dequeue C. Okay, and then I put the neighbors of C that haven't been visited yet. And how many neighbors of C are there? There are no neighbors that haven't been visited, so I will just put nothing. So now I have E and H. Then I dequeue E, and I put the neighbors of E. So the neighbors of E that have not been visited are F only. F is the only neighbor that hasn't been visited. So I put F, and I give it level 3. Then I take H out, and I put the neighbors of H that have not been visited. And how many unvisited neighbors does H have?
1.
Which is G. So I give it distance 3, and I put it after F. Then I take F, I dequeue F, and I put the neighbors of F that have not been visited, and that's an empty set. All the neighbors have been visited, so I put nothing. Then I put the neighbors of G that have not been visited, and there aren't any, so I don't put anything. Okay, so this is the BFS, the breadth first search. Okay. Now, if we continue, if we look at this BFS tree that we have constructed, the neighbors of B that we have enqueued are C. The neighbors of D, when we took D out, we put E and H. So we have E and H. And the neighbors of E, we put F. And the neighbors of H, we put G. So this is, level 0 at distance 0. This is level 0, level 1, level 2, and this is level 3. So this is not exponential. Okay, so this is level 2. Okay. Now, the point is this BFS tree is not unique. We can have multiple BFS trees. For example, if we had chosen to put H before E, we would have gotten a different BFS. So let's try that to make sure that we understand what's going on. Let's, here at this point, so everything is the same until we get to this point. We put D, but we put C, H, E. H before E. What will happen if we put H before E? Now, sorry, this is C, not G. So we have C, H, E.
Then we have H.
Then we take H out.
F, G.
Now we put the neighbors of H that have not been visited. And what are the neighbors of H that have not been visited?
G.
F and G. So we will end up putting F and G. So now F and G will be neighbors of H, right? So now you know, the BFS tree in this case will look like this. It will look like A, B, C, D, E, H, or let's do HE. But now the neighbors of H are F and G. F and G, then we take E out. Now what are the neighbors of E that have not been visited?
Nothing.
Nothing. So we will not enter anything, and we'll have F and G. So E will not have any children. So this is a BFS tree 1, and this is BFS tree number 2. They are different. Well, the only difference is here. The neighbors of H here, the neighbors of H, or the children of H here, are only G. Here we have F as a child of E. So basically the only difference is the parent of F. Here the parent of F is H. Here the parent of F is E. Okay? But the distances are going to be the same. So the point is, you know, even though the parent of F is different, the distance of F is 3 in both trees. So in all trees, the distance is going to be the same. And by the way, we're not giving a formal proof for this, but I'm assuming that it's intuitive, because we are looking we are looking at first at the nodes that are the closest to the source. Then we are looking at the nodes that are at the next level. In fact, this is BFS is a special case of Dijkstra's algorithm. So I will just wait until we cover Dijkstra's algorithm, and then we will give a proof of correctness, and that will imply the correctness of BFS, because it's a special case. Okay, so two different trees, but same distances. Now, one important observation is these nodes that still have an infinite distance, even though the algorithm terminated. What does this mean?
They're unreachable.
They don't have any edges.
Yeah, so they are unreachable edges. So now this algorithm then helped us find or identify the reachable edges, the reachable vertices, sorry. So all the vertices that have finite distances are reachable, and the vertices that have infinite distances are unreachable. So the algorithm identified these unreachable vertices. Of course, if you are only interested in identifying or identifying reachable vertices, you can use any kind of traversal. It doesn't matter. You can use breadth or depth. If all what you want is to determine if a certain vertex is reachable or unreachable, you can use any traversal. But if you are interested in finding the minimum unweighted distance, then you must use breadth, BFS. Okay, so any questions on this? Okay, so since there are no questions, let's let's look into the code and analyze the algorithm. Okay, so let's write the code for BFS. BFS, our input is going to be a graph in adjacency list form and a source. So what will be the first step? Just translating this into code, what should the first step be? What did we do first? What's that? Say that again.
We are keeping all the distances as infinity.
Yeah, initializing all the distances to infinity except for the source. So what we do is for each vertex u in G, u dot d equals infinity, and then source dot d equals 0. So now just we need to explain this notation and the assumptions here. So we are assuming that this graph is represented as an adjacency list, which means that to traverse the list of vertices, we are traversing an array. Right? So in this case, the adjacency list representation of this graph, we're not going to show the whole thing, but we'll have A, B, C, D, E, etc. For A, we have B and D. For B, we have C. For C, we have nothing. For D, we have A, E, and H, and so forth. So now this loop here goes through the array. It doesn't go through the lists in the array. It only goes through the array and sets. It assumes that each vertex has an object that represents it, a data structure. You can think of it as an object. And in that object, there are multiple data fields. One of these data fields is the D, which is the distance that we're trying to compute. So it's setting the field D in the object of each vertex to infinity. Okay. So D is the distance. And for the source, it's setting that to 0. Then what should we do?
Put the source in queue.
Okay, so we have to create a queue first. So create a queue. Then we do q.enqueue of S, the source. Then what?
Then dequeue it and enqueue the neighbors.
Yeah, then dequeue and enqueue the neighbors. But this is something that we will not do once or twice. We will be repeating it for every vertex until, what's our termination condition?
Queue is empty.
The queue is empty, exactly. So we terminate when the queue is empty. So while queue is not empty, do u equals q dot dq, and then for each vertex that we dq, we first set the distance. We go through the neighbors. For each neighbor, v in the adjacency list of v in the adjacency list of u. Okay, so I will skip something important here, then we'll figure out what it is. I'm going to do v dot distance equals what? I'm going to set the distance of v. So u is the current vertex, v is the neighbor. Distance of v is equal to?
U dot d plus 1.
Yeah, u dot d plus 1. And then I'm going to nq, q dot nq of v or u, nq the neighbor or the vertex that we have just dq'd. Obviously, we don't want to nq the vertex that we have just dq'd. We want to nq the neighbor. Okay? Now, what's the important line that I missed here?
Check if u dot d is not in.
Yeah, say that again.
If you have already visited that particular vertex or not.
Yeah, so we want to do this if the neighbor has not been visited. So if the distance of the neighbor is, so here we add this, if v dot d equals what? Infinity. Yeah, if it's infinity, do this. If it's not infinity, do not do anything. So infinity means unvisited or undiscovered. Okay. So this is the BFS algorithm. It's a straightforward algorithm, but it has some it's a very useful, it's very powerful, in fact. And what we are doing here, we will be doing similar things with other algorithms, like going, processing one vertex at a time and going through the adjacency list of a given vertex. We will be doing this with lots of algorithms. Now, one more thing that I would like to add is tracking the parent of each vertex in the BFS tree. So the parent can be tracked. So in addition to the D field, I'm going to assume that I have a parent field, and I'm going to call it pi for parent. So D is distance, and pi is parent. So I'm going to set u dot pi to null. Now, where do I set the pi to the actual value in the algorithm?
When you're enqueuing it.
What's that?
When you're enqueuing it.
Yeah, when I'm enqueuing. So here I set the v dot pi to v dot pi equals
U.
V dot pi. So u is the parent of v. When you are doing this processing, u is the parent and v is the neighbor. Okay. Okay, so in fact, here we drew two different BFS trees, and in each tree, a node can potentially have different parents. Now, how many different BFSs or how many different trees can we have in general? Can you think of a worst case scenario for that will give you a large number of traversals, of BFS traversals or BFS trees?
Single linked, maybe?
Yeah, what?
One, did they just go on a line to each other, basically a linked list?
Mm-hmm.
Probably be one of the worst cases.
Okay, yeah, well, that's, yeah, so if you have this,
You would have branches on them.
yeah, so in this case, well, if for a given, well, in fact, if for a given source, in this case, you only have one tree, right? It's so it's, but yeah, for a given source, if you fix the source, then you only have one BFS tree. You can't have any other tree. You always have one option, but you will have more options when you have more edges or fewer edges. Yeah, when you have more edges, you will have more options, right? Yeah. So it's, for example, if you have a complete graph, so if you have a complete graph, A, B, C, D, and suppose that your source is A, right? So in this case, you will have your source is A, and because it's complete, all of them will be children, can be children of A, but in which order? So you can do A, B, C, D, but you can also do A, because you can always, here you can do B, then C, then D, but you can do C, then B, then D, and you can do all different orderings. So in fact, you have, in this case, you have n minus 1 factorial of BFS orders, right? You have n minus 1 factorial of different BFS orders if you have a complete graph, or V minus 1 factorial. Because each one of these is a different BFS. It's a different ordering. Choosing to visit B before C will give you a different traversal order than you choosing to traverse C before B. Anyway, so it's, in fact, with more edges, you will have more options, and the number of different BFS traversals is huge. Okay, now let's analyze the algorithm. When we analyze graph algorithms, we analyze them in terms of V and E. So we have two input parameters. V is the number of vertices and E is the number of edges. And are these parameters dependent or independent?
Independent.
They are independent, yes, because you can have lots of vertices and very few edges, and you can have lots of edges and very few vertices. You can have anything. You can have any combination of too many vertices or too many edges. For example, too many vertices. You'll always have the the number of vertices A, B, C, D, for example. For A, B, C, D, you can have a complete graph, and you can have a completely disconnected graph. So this is a graph. This is a graph that has 0 edges in it. And the other extreme is a complete graph. So the number of edges has nothing to do with the number of vertices. They are two independent variables. So that's why when we analyze a graph algorithm, we express the asymptotic complexity in terms of two variables. V and E, because they are two independent variables that represent the input size. So for graphs, the input size is not a single number. It's two numbers, the number of vertices and the number of edges. Okay, so now, most of the analysis is easy. So this loop is obviously what?
Theta V.
Yeah, so this is theta of V. And here, this is constant. We don't have to worry about this. This is constant. This is constant. Then we will get to this loop. So now in this loop, how many times will this line get executed? V? Yeah, so it's how many times will a vertex get DQ'd? Can a vertex get DQ'd more than once? No, it cannot, because we're doing this. So we NQ it once and DQ it once. So at most once, but it could be 0 times, because these did not get DQ'd, the unreachable ones. So we say that this is O of n. O of V, sorry. So this is O of V for this line. Now, the key in this and analyzing this algorithm is counting the number of times this line in blue is executed. Now, for each vertex, the line in blue will be executed for each element in the adjacency list. So in fact, across the entire or throughout the entire algorithm, the line in blue will be executed by the sum of the sizes of the adjacency lists, right? So for vertex 1, it's going to be the adjacency list. So let's draw this again, because we have a space problem on the board. B and C. So A has B and D, and B has C, and C has nothing, and D has, what does D have? It has A, and it has E and H. This is not, doesn't look like a good H. Okay, so now when we process A, we will go through these. When we process B, we'll go through these. So the blue line will get executed this number of times. When we process C, this will not get executed, because the adjacency list of C is empty. When we process D, we will do 3 times, because there are 3 neighbors. Now the key idea is that the blue line here will get executed whether the neighbor gets NQ'd or not. So whether we NQ or not, we are going to execute the line in blue. So in algorithm analysis, we count all the operations. And our asymptotic complexity, in fact, is determined by the most frequently executed operations. So clearly here, the line in blue will be executed more frequently in general than NQ. They could be executed the same number of times, but in most cases, the blue will be executed more frequently than the NQ, right? So what's the sum of these? What's the sum of these? So for A, we will execute it twice, for B, once, for C, 0, for D, 3. If we sum all of these for all vertices, what will this give us?
Number of edges.
Yeah, it will give us the number of edges. But if the graph is undirected like this, will it give us the number of edges, or
Twice the number.
Yeah, twice the number of edges, or twice the number of edges for twice the number of reachable edges. If we want to be precise, so for example, in this example, each reachable edge here, and reachable edges are all edges except this edge. This is the only unreachable edge. All reachable edges were processed twice. So when we looked at the neighbors of A, we processed this edge. And when we looked at the neighbors of B, we still processed this edge. We ended up not enqueuing, so we ended up not executing this. We did not enqueue. We did not execute this, but we still executed the line in blue. Okay? So in fact, this is going to be, limited by 2e. So this is going to be 2e or O of e. But it's O of e, it's not O of e for every vertex. It's O of e in aggregate throughout the entire algorithm. So this is an aggregate analysis. So this is in aggregate, which means that the total running time is not going to be v times e, because this is not e for every v. It's e for all v's, not for each v. Okay, so if it had been e for each v, we would have multiplied e by v. But here this is not the case. It's not e for each v. It's e across the entire algorithm. So then what will be the overall running time?
V plus.
Yeah, it's going to be v plus e. Because we know that we will have a v and we will have an e. So it's the sum of the v and e. So the running time is O of v plus e for BFS. So it's linear. It's a linear algorithm. The asymptotic complexity is a linear function of the two variables that represent the input size, which are v and e. Okay. So any questions on this? So here it's 2e if the graph is undirected, but e if it's directed. So 2e if it's undirected, and e if it's directed. Because the directed edge will be visited twice. Sorry, if it's undirected, then B will appear in the adjacency list of A, and A will appear in the adjacency list of B. But for directed edges, no. So if we make it directed, then B will appear in the adjacency list of A, but A will not appear in the adjacency list of B. Okay. Any questions on BFS? Yes?
While creating the adjacency list, are we not gonna add A as the adjacency list for B?
I'm sorry.
Since it is an undirected graph, while creating the adjacent nodes of each vertex there, so we might also need to add A in the adjacent list for B, because it is also a neighbor for B.
Oh, yes, you are right. Yeah, you are right. You are absolutely right. I missed that. Yes. Yes, you are absolutely right. Yeah, so in the adjacency list of B, we'll have A. And thank you for catching this. Yeah. Yeah, I think in the first adjacency list that I drew, I think I put A in there. Yeah, but yeah, you are absolutely right. Okay.